Hello again. Welcome back to the Curious Cube.
Today we'll be discussing some ideas that are a bit more philosophical in nature.
So let's get started with the first question.
Our first question comes from Jess, who asks, what defines each main area in math? Algebra, combinatorics, number theory, and geometry. What defines math as a whole?
So, in my opinion, I think mathematics is really about the discovery of patterns in an axiomatic world. And what I mean by that is it's distinctly different from that of science because in science, you're trying to make claims about the physical world. And the axiomatic world, I guess the one in which you have mathematical rules laid down for you, is definitely one that doesn't depend on our physical world. What do you guys think about what the definition of mathematics is?
Well, there are a lot of opinions about this. Like, I mean, it, like, it, you definitely have, I guess, the logic playing a big part in it. But it definitely, like, in its most essential sense, it's kind of abstract, that it isn't really connected to the real world, like you said. But like it involves like making logical deduction and applying it, like I guess like applying logic to get results about numbers or other mathematical objects. But that definition is a bit of a tautology because I haven't told you what a mathematical object is. So I'm sort of cheating with that definition there. But, circular reasoning, don't do it in real life.
I don't know if there's like a real way to define math as a subject. I think it's definitely connected to like the definitions that they gave. But I also I'm trying to think of a definition that has less fancy words. Because like if you're anyone like me, then like a good portion of those words kind of went over your head, which same. I I guess math is like the study of, I want to say numerical values, but also that's kind of general. Uh it's just the whole study of math is so broad that I don't think there's a single thing that can pinpoint it. So how about we look at like the distinct areas of math?
Sure. Yeah, I want to reiterate that, in my opinion, math is really just patterns. Like, finding patterns in structure is essentially what mathematics is. And for each of the main areas of math, algebra, combinatorics, geometry, and number theory, I think you can see evidence of how mathematics is really just pattern finding. So if you look at number theory, like I think number theory is really just finding patterns in the natural numbers 1, 2, 3, 4, etc., etc. Like you can make statements like prime number theorem, for example, which quantify the patterns in the primes. And I guess moving on, geometry is like finding patterns within shapes, like which three lines in a triangle concur, for example. Combinatorics is finding patterns in discrete objects. I guess I won't really define what discrete is, but I feel like combinatorics is just where you throw everything that's not algebra, geometry, or number theory. And then, yeah, algebra, finding patterns within specific structures that have like specific operations and relations. I guess that was really, really vague because algebra in like at the college level, it definitely looks a lot different than what most students think of algebra in high school.
Yeah, you're not going to be doing the quadratic formula when you're in like a real
Yeah,
analysis
definitely.
class.
There are some things that I there are some things about the premise of this question that like maybe they work pretty well for math olympiads, but they don't necessarily work quite as well if you're talking about like the really advanced college level stuff. In that like splitting math up into algebra, combinatorics, number theory, and geometry, like that works pretty well when you have something like the IMO shortlist. But then like there's sort of more to math as a whole that doesn't really get encapsulated with that when you look at like the more advanced stuff, like topology. If you have like some weird n-dimensional torus with multiple holes in it that you stretch around, like it's like maybe you could class it under some type of geometry, but it's not the type of geometry you have on a math contest of like, here is a triangle, here is its orthocenter, whatever. Like it's not the type of geometry you think of when you hear the word geometry. Or, other stuff like real analysis or complex analysis. Like maybe they would fall under the Olympiad subject of algebra, but like the subject that mathematicians call algebra is sort of not really to do with anything that you would see at the high school level very much, in that it deals with these like structures like groups and rings and fields and such, which is like the study like whereas at maybe an Olympiad level, maybe you just have like stuff about polynomials or about inequalities or like functional equations, where it's like, well, maybe inequalities to some extent are more the domain of real analysis. Polynomials maybe go under real analysis or some sort of, something.
I think this is like
Maybe.
algebra, right? Because you can consider
It
things like
depends.
polynomial rings.
And then like,
But a lot
Depends
of
how you
things
treat
don't
them.
get- A lot of things just don't get
Yeah,
fit into like these.
that's another
nice
thing. Like
categories.
sometimes like what you have a piece of math that doesn't necessarily fit very well. And going back to what I said about Olympiad algebra, functional equations sort of just don't fit very well, like at all, very much. Maybe to some extent, depending on what they are.
What
Maybe
even are they?
some of them
Hot take: functional equations are puzzles, not math.
puzzles are math.
I can
Puzzles
agree with
are
that hot
math,
take.
depending on. Yeah, I think puzzles are math, but
It's
going back to what I was
sure.
saying, like, that's sort of another thing, is like you don't really have a division of math into areas so much when there can be some amount of like overlap, like some things feel like combinatorics but also like number theory, like there can definitely be some amount of overlap. So like a lot of the like dividing it up into areas can be useful, but the areas are not necessarily going to be like exhaustive, or no, like the areas are not necessarily going to be disjoint. They can like have overlap, and the areas are maybe not going to be exhaustive necessarily, if you have like weird super advanced stuff like partial differential, like maybe with enough squeezing, like maybe with enough fudging around, you could try to say that all of math fits under algebra in the Olympiad sense of the word, or combinatorics or geometry for some sense of the word, or number theory, but like
everything is everything
that's
is
not the same way that
math.
mathematical research would do it, and like in particular with geometry, like if someone is doing research in geometry, they're doing like hard stuff that I'm not very qualified to tell you about, but they're not like drawing a triangle and then drawing its circumcircle and then doing something like a lot of the problems on math contests about geometry, like they're maybe very interesting and nice, and like they can be really neat, but maybe to a mathematical researcher, like it would not be very interesting maybe if you could just like just take a computer and be like, if you're a researcher, you have no reason not to just take the problem and just bash it with complex numbers. In a contest, you can't use a computer to just bash the problem for you. But if you're a researcher, you can just be like, okay, sure, I'm just going to kill the problem with complex numbers because my computer can do all the computations for me. So if you can just do it by computation, it is maybe not quite as interesting. But some stuff is,
Yeah, I guess this kind of goes without saying, but there's a lot more to math than the stuff that you find in Olympiads. Olympiads, I think what they really teach you is like, the kind of like problem solving techniques and problem solving mentalities that come to help you later on. Though, of course, there's a lot of things that you learn from Olympiads that you don't learn from school that help you later on, and blah, blah, blah. It's like a nice little intermediary.
And to some extent, it is like a lot the same. Like Olympiad combinatorics is maybe not that different from some aspects of research combinatorics, except that the research problems are like harder.
So our second question is from S, who writes, name a key concept in math that has shaped how you think of it as a whole or has helped you monumentally.
This is kind of a basic-ish example, but when I first learned about complex numbers, There's probably more like groundbreaking eureka moments in math to look for, but for me, like seeing like the basic number line that you see in like every elementary school classroom, or at least every elementary school math classroom, turned into like a 2D like coordinate grid that has like all every complex number. It just showed me like this way of visualizing numbers, or this way of visualizing like complex numbers that's like it turned from something that I had known for like a very long time to something that I could like really visualize that I could use to visualize a more challenging concept.
Yeah, so I think one of the key concepts in math that I guess students seem to start to realize later on is that math is really a lot of it is really about generalization, and you can kind of start to see this when you do contests. Like maybe you solve a problem on the AMC or AME or on an Olympiad, and then like you solve the problem, but then you're still left wondering maybe could something stronger be true? Is the problem, does it follow from a more general statement? And this kind of mindset is not unique to contests. Like this is just present in all of mathematics. As an example, like I guess you can think of things like fields as generalizations of like the real numbers and complex numbers. And then same thing with groups. You can think of groups as generalizations of, well, like things in modular arithmetic, for example. And like you can even generalize the generalizations. Like you can look at the structures inherent between groups, like the relationships between groups, and then the relationships between vector spaces in linear algebra, and then like the relationships between like objects in topology, and then you can all make connections between them, and then you get category theory.
When I first learned about group theory, it was just like this, like a very general version of like the about of like functions and or not. I don't know functions, but like of like concepts that I had learned from like just your standard math. So it was really interesting.
uh, I imagine there are. I'm not. I'm not thinking of any really great answer to this at the moment. Maybe some things were like a long time ago, and I don't necessarily remember them well. I mean, yeah. But I mean, I'm not. Yeah. Shrug.
I guess for you there's not like a single thing that like helped you. It's like it's all like cumulative.
There has been a lot of it. You know.
You know that the Amy is right around the corner. We have this question from Victoria. What are some helpful strategies you would recommend for Amy and AMC preparation?
So, in my opinion, I think one of the helpful strategies that's like sometimes overlooked, in my opinion, is definitely check your work for mistakes, especially if you're a person who's prone to making errors. And one of the ways that I personally myself combated mistakes is to like check my computations and thought process for a problem immediately after I solve a problem, because personally I found that when I came back to a problem at the very end of a contest, I would usually feel more pressure. And also, I would rush checking my work for the problem and like maybe still miss the years I made the first time. So that's my tip for helpful strategy.
Yeah, on the topic of making errors, there was a time when I got a 12 on the AME, and the problems I missed were problem 3, problem 4, and problem 5. This really happened. So yeah, I have definitely had my fair share of making like silly mistakes. Um, so yeah, that's definitely a good one to want to avoid. Um, you know, so yeah, be careful about your calculations. Don't accidentally like leave out a factor. Like, there was one time when I missed a problem on the AME because I like solved a quadratic equation wrong when I like, messed up completing the square on a quadratic that I like left out a factor of 2 somehow. Don't, you know, and you like be, I've heard it said that you should make your scratch work neat. Um, and like look at all the problems just in case like I've heard it said, and I definitely agree, that you should like look at all the problems in case some of the last few are easy, like unexpectedly easy. yeah, like, and like, I guess, try not to like think you have to like also I've heard it said that, maybe if a problem is harder than you expect early on, like be willing to skip around. In general, actually, this is just a more general thing that applies especially to Olympiads, but it also can apply to the Amy, that like people should be willing to skip around, because just because someone thought the problems were in order doesn't mean that they got the order right. And even if they did get the order right in the sense of what most people are going to solve, like what most people solve might not be the correct order for you. I guess this especially applies if you have like strong preferences for one subject over another. But I guess if you have that, like if you're like much better at geometry, for example, like you probably already know that, so you don't need me to tell you. But yeah, so yeah, I've heard it said like you should be careful, being aware of easy problems later on or hard problems early on. Yeah, so but that's I guess that's more. These are more strategies for like actually during the test.
Mhm.
But I guess like that's all we have to give you now, because if you're like preparing for the Amy, like there's not that much you can do with like 1 or 2 weeks before the test.
Yeah. I remember there was a year that there was an Amy number 6 that was way harder than the problems around it. There was an AMC 12 number 12 that was a lot harder than the problems around it. And then there was another year where both of the number 14s on the Amy 1 and 2 were like substantially easier than the problems around it. So go figure, these like the people who order the problems, problem difficulty is when it comes to like differences between consecutive problems, like at that point it kind of becomes a bit subjective. So
Yeah, definitely.
I have a personal tip for avoiding sillies, and this kind of only works if you work fast. And I think these are the kind of people who tend to make sillies the most. Like if you're like very fast, but you tend to make a lot of computational errors. Then on a slow comp test on the Amy, I would suggest rewriting the entire way you did the problem just neatly and on like a plain sheet of paper. And I did this during one of the Amy's. I had actually finished the first like 10 or so questions like relatively quickly, and I wasn't quite ready to like take on the other questions yet. I guess I was like a bit brain fried, so I decided to just check my work by like meticulously writing out everything like as neatly as possible. And like, yes, that is a huge time sink, but I caught like 3 sillies in the process, so I would say it was worth it.
Relatedly, you should like use a separate sheet of paper for every problem. Like use a lot of paper,
I
Kill the
also only
trees!
use one side, because if I use both sides of the paper, I find myself flipping over all my scratch paper to find where I wrote something.
Mhm.
Oh yeah, and it helps
do
if
that
you
too.
have like a large table. It's nice to have
Oh
a big
yeah.
table.
Like as soon as she says, I don't think too many schools will have like. I totally get schools having like a ton of AMC takers. Mine definitely did, but at the Amy level, there should be like relatively fewer. So do not settle for one of those little lap desks. Those like they don't roll. If you're trying to draw a big geometry diagram, don't settle for less. Get a big table. Just like ask very nicely, and your teacher might relent. Or maybe there's not if there's like space constraints, but generally in like a classroom you could just have like a desk. Hopefully you're not stuck with the little lab desks. If you are, then good luck.
Also, like when I said, "Oh, it's maybe a bit too late to do very much on Amy prep," like it is maybe you could maybe spend at least a little time thinking about Olympiad prep, since that is in more like 6 or 7 weeks. And so, like for this, I've heard it said, and this time I guess I'll actually credit where I've heard it. Like Evan Chen has said some things. Like you may know who he is. He's, among other things, he is or was the like co-editor in chief of the USAMO. He has said like, don't be scared of Olympiad style problems. Like you should be like, give them a try, that it's not super scary to, oh no, I have to write up a proof. Don't be scared of that. Just like, explain what you did. And and that's basically a proof if like, if your logic is correct. But,
Yeah, we'll
so
definitely be talking a lot more about Olympiad problems as the season rolls around. But if you're ever kind of out of Amy problems to do, you should try out Olympiad problems. Partially because they aren't that different and they're not as scary. Partially because you should get used to it, and partially another because shooting like higher, like shooting for the difficulty above what you're doing currently is like a good way to get better and then see how and like improve your thinking skills at the very least.
and
yeah, I
also
think one thing. Oh yeah.
yeah, go ahead.
All right, sure. I think one thing that like helps with Olympiad problems is like if you write up solutions to Amy problems, this will like automatically like make your Olympiad skills better, even though Amy problems are not proof style problems, because you have practice explaining your solutions or your line of reasoning.
And also another thing is like, doing Olympiad problems might help with the Amy, like in a larger sense, in the sense that like, like I don't know if it was last year or the year, like there was some Amy problem recently where like the solution involved Simpson lines. And like, if you only did Amy geometry and you're more used to, like just coordinate bashing or whatever, maybe you would be hard pressed to do that one. But like, if you're used to a little more used to Olympiads and you're like, oh, maybe I can, oh, it turns out that's a Simpson line. So such and such points are concyclic, blah, blah, blah. Then maybe you're, better equipped to solve that problem and then you'll do better. Maybe.
As a seasoned coordinate basher, I'm offended. I'm kidding.
So yeah, like, just, yeah, just, giving, and, and it's, also good, like if you surprise yourself by making an Olympiad, or if you don't surprise yourself if you were expecting it, like, you're better prepared. But yeah, I think it's like, it's nice when there are contests that are easier proof based style. In fact, there is the USAMTS, if people don't know about that is like a contest that exists, which actually is an alternate path to qualifying for the Amy, but not with a very like high score.
USA Mathematical Talent Search, I think.
Yeah, it's a longer proof style contest, which is nice if you don't like short time limits. But yeah, I wish there were more contests that had like easier proof style problems, but there aren't, because proofs are hard to grade accurately. And there are not a lot of people who like are really good at it.
So to those of you who are taking the Amy, good luck and enjoy the problems.
For our next episode, we'll be moving in a more mathy direction, so please send in questions about any mathematical topics you might be curious about, especially topics in more advanced math.
You can also send in questions about how problems from MEA contests like the AMCs might hint at some deeper mathematics hidden under the surface.
See you all next time, and stay curious.